time, we continued our lecture on heat, energy, and temperature, which was the last thing that's going to be covered on the exam. We're going to go over, finish up that lecture today, and that'll probably take the rest of the time. So some of the problems we do today are going to be relevant for the exam. So if you've looked at the practice exam, you'll see, I think, question 21 on the practice exam is a heat capacity specific heat question. Right, so we talked about the different temperature scales. Right, and what were the three temperature scales that we were familiar with or that we use? Degrees Celsius, degrees Fahrenheit, and Kelvin, right? Kelvin was the absolute temperature scale, meaning absolute Kelvin means zero energy of the system, doesn't exist. Celsius is related to the states of water, right? 0 Celsius is when water freezes. 100 is when water boils. And then we talked about how the different ways to measure, temperature, right? So we use a thermometer. We look at properties like expansion of a fluid or a solid as you heat it up, and that's correlated to a change in temperature, right? And the temperature was what is the temperature related to in terms of energy of the atoms and molecules in a substance? Yeah, the average kinetic energy, right? So temperature is proportional. That's what this means. This little fish symbol is proportional to the average kinetic energy of the substance. Right, that just means like how fast or much are the molecules or atoms vibrating or bouncing around, right? And so you think about temperature, things should be bouncing around more, right? So they're moving around faster, the temperature goes up. Okay. And we talked about the difference between temperature, kinetic energy, and then the heat of a system, right? So the other thing we talked about was Q, which was the heat or energy of the system. And that heat is related to what types of energy? It's going to be in units of joules, right? So units of joules for Q. A joule is the standard unit of energy. And then what was Q related to in terms of like kinetic potential energy for the particles in the system? It's the total, this is the total kinetic and potential energy, right? So the heat is related to the sum of all the kinetic energy and the potential energy. We talked about, potential energy is like when you have a ball above the ground, it has a lot of potential before you release it. As you release it, the potential gets converted into kinetic energy, and then it hits the ground and stops again. Right? In atoms and molecules, that potential energy is stored in the bonds between atoms, molecules, and what makes up the atoms. And so the heat is related to the total of all those different types of energy added together. And then we had an equation that related to how much heat, the movement of heat, right? And so energy, according to the first law of thermodynamics, cannot be created or destroyed, just transfer from one form to another. And so then we looked at how does heat transfer between substances. Intuitively know if we have something hot next to something cold, heat moves from which direction to which direction. Right, like what do you think if you have something hot touching something cold, what happens to both things? So if you have boiling water and you leave it in the air, right, the boiling water is hotter than the air around it. Eventually what happens to both things? Yeah, they reach the same temperature, right? So heat moves from one to the other. So in that case, the hotter substance, the boiling water, transfers energy to the air around it. And so the heat then moves from the hot thing to the cold thing, right? So intuitively we have a feeling for that just from everyday experiences. But we had a direct relationship that allows us to calculate how much heat is transferred. And this is kind of where we ended off talking when we discussed the Bohm calorimeter, right? How we determine the amount of energy that is in all of our foods, right? Does anyone remember what this equation was? Mass times the specific heat times the change in temperature, right? So the mass was the amount of stuff that we are heating up. The specific heat is a physical quantity of that substance, and it tells us how much energy is required to raise 1 gram of that substance by 1 degree Celsius or Fahrenheit. All right, so the units of the specific heat, right, again, we use these brackets sometimes to mean units, are going to be energy over mass times temperature. And it makes sense from our equation that that's what we get, because if we know that heat is measured in units of energy, then this quantity here is multiplied by mass, multiplied by temperature. So to get units of energy, we need units of energy divided by units of mass and temperature so they can cancel out, and all we're left with is units of energy. And then again, this is a specific property of the system, right? So the specific heat of water is going to be different than the specific heat of iron. If something has a lower specific heat, does it take more or less energy to heat something up? It takes less, right? So there's a lower specific heat, that means it's going to heat up faster and it's going to cool down faster. If it has a low specific heat, it's going to cool up slower but also cool down slower. And how do we remember that? Well, an iron pan has a lower specific heat than water. When you heat up or you try to boil water, the pot is going to get hot a lot faster than the water inside. It takes longer to heat up the water, but the water also stays hot for a lot longer than the pot. Because it requires less energy to heat up the metal than it does to heat up the water. And again, we'll talk more about why that is, but it's related to the metal. The atoms are more tightly bound to each other so they can transfer energy easier. Okay, and then the last thing that we talked about was, in energy and nutrition, we can measure the amount of energy that's in a food sample using what's called a Bohm calorimeter. So let everyone finish writing. And what the Bohm calorimeter does is, we don't know the specific heat of a sandwich, right? It has a bunch of different stuff in there. It's hard, you'd have to know the specific heat of all the different components of the sandwich. Those are made up of cells. They have proteins and fats and lipids and stuff inside of them. So it'd be hard to directly measure the specific heat of everything in your sandwich. But you can take advantage of the first law of thermodynamics, which is that energy can't be created or destroyed. So what you do is you take a sample of food, you ignite it, right? So that's where the Bohm part of the calorimeter comes from. You ignite it, that causes a chemical reaction that then releases heat, right? It releases energy, and you know that energy has to go somewhere, right? It can't be created or destroyed. So the energy moves into the surroundings around it. So what do? You put it with water. You know the specific heat of water. You know how much water you put in there. And then you can measure the change in temperature of the water. So that allows you to then solve for how much heat the water absorbs. And because of what we said from thermodynamics, that can't be created or destroyed, the amount of heat that the water absorbs has to be equal to the amount of energy that was in your sample. All right, so you get this relationship that the amount of energy that's absorbed by the water just has to equal the negative whatever was released by the food. And what does that do? That allows you to then solve for the amount of energy, which is measured in units of joules, or commonly in nutrition, units of calories. And so we're taking advantage of thermodynamics, this relationship between heat absorbed, and then using them to set up an experiment to calculate the energy absorbed by something. So I believe question 21 on the practice exam goes over this very example. All right, any questions on where we ended up last time?
Is there a standard value for
So there is going to be a standard value, but it's dependent on the substance, right? So for water, it'll be 4.184 joules per gram degrees Kelvin or degrees Celsius. But if it's metal, it's going to be a different value. So that's a physical property, right? So S is a physical property of the material. So theoretically, you could use anything for a bomb calorimeter as long as you know what that value is, right? So people, they, spend their dissertations and stuff determining values of S for different materials, right? So you look up and you'll find something like, let's see, where was it? Something like this in a textbook or on online databases and stuff, and they'll give you, based off the material, what is the specific heat of that substance going to be. And you know that these are all different molecules, they're solids, some are liquids. The values you calculate tells them for each of these how much energy is required. So this says you need 0.488 calories to raise ammonia, 1 gram of ammonia by 1 degree Celsius is what this value is telling us. Does that make sense? Where did I end off at? Okay, so that's where we ended off with, right? The bomb calorimeter. And the calculations of heat can get slightly more complicated. And today we're going to talk about, well, how do we take into account when we change phase? So when we go from a liquid to a solid or a solid to a liquid and vice versa. But first, before we do that, let's do a unit conversion problem because this is going to be relevant for our exam on Wednesday. So here we have a 2-ounce serving of pasta, and that provides 200 calories, right? What is the energy value of pasta in calories per gram? And so this is uppercase calories. So this is going to be a unit conversion, and so we can all use practice with unit conversions. This is what our quiz is on. That's still going to be on the exam on Wednesday. And so we have a couple of conversion equalities there, and then we need to convert our energy value into uppercase calories per gram. So why don't you guys think about that for a minute or two, and then we'll go over it together. Those of you that are stuck, maybe we can help you get started. So we have a couple conversion equalities, and those give us conversion what? Factors, right? And those are going to be the ratios that we get from the conversion equalities. So just from what's given here, we can make a couple conversion factors. So what are the conversion factors you can get from these two equalities? Yep, we get 1 pound. And remember, one thing I noticed on the quiz is we always have to write our units, right? We write our units, it's easier to keep track of what we're doing, right? And then we get the inverse, 16 ounces per 1 pound. Then from the other one, we get 454 grams per 1 pound. And then 1 pound per 454 grams. And we know which one to use based off of the units we're going from and which ones we're converting between, right? And we know we want to start, right? So it's kind of difficult because this one we're starting from a ratio and we're going to end with a ratio. There are different ways that you can do this. I'm going to show you one way. If you guys find another way that works and gives you the same answer, that's fine. Is we're going to start from a value of calories over ounces, right? So the problem gives us that for every 2 ounces, we have 200 calories, and we want to convert that into calories per gram. So we're going to start from 200 uppercase calories, and we don't have to do this for this problem, but just so you guys know, 1 uppercase calorie is equal to 1 kcal, which is equal to 1,000 lowercase calories per 2 ounces. This is where we're going to start from, and we want to end from, we don't know the numbers yet, but in calories over grams. So we can go from a ratio, or we can convert masses right away. And so we're starting from ounces, and we want to get rid of these ounces in the denominator and turn them into grams. right? So we're gonna go from ounces to pounds to grams, right? This is kind of the conversion. But this is all gonna be happening in the denominator, which is the same principles from what we've done before. Right, the same ideas with writing our conversion factors, but we just want the units to cancel in a different way. All right, so that's kind of where we can start off from. Let you guys think about that and continue working. So first, we're gonna convert the ounces in the denominator into pounds. So which conversion factor are you guys gonna use, the left or the right? All right, so think about what units do we want to cancel out? The ounces, which means that the ounces should be on the same side of the ratio or on the opposite side, meaning denominator. It should be on the opposite side, right? That's how things are going to cancel out. So if we put in the 16 ounces over 1 pound, now we see ounces here cancels out with ounces there, right? So that's how we know, even though we've been doing conversions a lot of time, where they're on everything we want to cancel out is in the numerator, here they're in the denominator, we just want them on opposite sides of that ratio. So that's our first conversion factor. And then we want to go from pounds to grams, right? And so from pounds to grams, which conversion factor do we use? The left or the right here? The right, because you want to leave with grams in the denominator. So that's going to be 1 pound per 454 grams. And now we see the pounds cancels out here, pounds cancels out here. All we're left with is units of calories and grams. Calories over grams, which is exactly what we want. So we plug that in, we get 200 times 16 divided by 2 times 454. Right, so this problem we can assume that everything non-one number is going to be our significant figures. So we have 200 calories, that has how many sig figs? 1, right? So that's already the least amount of sig figs that we can have. So 2 ounces also has 1 sig fig. And then how many sig figs is in 454? 3 and 16? 2. So the least amount that we multiplied and divided there was how many sig figs? 1. So our final answer should have 1 sig fig too. So this should end up being 4 calories per gram, right? So we just multiplied everything and divided everything. So what do we put in the calculator? I'll write on a separate part, a different color. In calculator, what we put was 200 times 16 times 1 divided by 2 times 1 times 454. And that was the number. That's what we reached this number for. Really, it came out to like 3.5 something, but because we needed to round it, we rounded it up to 4. That sounds about right, because that's about as many calories as you get per gram for carbohydrates. All right, any questions on that? Or unit conversion?
So the sig figs that we take into account is the ones that we are using when the problem starts?
Yeah, so for example, if you're ever given a problem where you have to go, one step you have to go between grams and kilograms, but that isn't given to you, you just have to know that. You wouldn't consider those in the sig fig calculation. Yeah. It's generally just the values that are given to you.
Okay.
And if you're given a conversion equality like this on the exam, like I'll usually say whether or not I want you to consider that sig fig value or that sig fig value. Yeah, on the practice exam you see like, okay, I want you to consider these values, don't consider these other values. In general, in a problem, anything that's a conversion, you really don't have to consider for sig figs. It's really just the numbers that are given to you. So if you ever see that on a standardized test, that's where that comes from. All right, so this is a unit conversion using units of energy, right? And so as we go on in the course, you'll see more of these conversions between quantities that are already given to you in ratios, right? So we have to be comfortable with going between single dimensions, right, like meters, maybe to miles. That's one conversion. or comfortable going from a ratio of calories per ounce to calories per gram. Or we could have changed from calories per ounce to joules per gram, right? That would have been two different conversions you have to do. All right, any other questions on that? All right, so here we have a calorimeter problem. So I'll let you guys think about this one. You have a 2.3 gram sample of butter, and it's placed within a bomb calorimeter containing 1900 grams of water at a temperature of 17 degrees Celsius. After the complete combustion of the butter, meaning you've burned up all the butter, the water temperature is at 28 degrees Celsius. What is the energy value of butter in calories per gram, right? So you want to solve for the energy value, and you want to solve for it in units of calories per gram. So there's two steps to this problem. One is a bomb calorimeter, and the other one is kind of looking at how do we turn that energy value into a ratio of energy per unit gram. And so what's the relevant equation for calculating the energy value within your sample of butter? Q, it's related to Q, right? So we need to use Q, which is equal to the mass times the heat capacity, or the specific heat, those are used interchangeably, times the change in temperature. All right, so how are we gonna determine what values we need to use for this?
Well, water's already given.
Yeah, water's, it'll be given to you, so I'm gonna give that to you right now. Joule per gram degrees Celsius. You need to determine what delta T is.
The final mass.
Delta T is always equal to T final minus the initial temperature. We have 28 degrees Celsius minus 17 degrees Celsius equals 11 degrees Celsius. All right, so for the energy value of butter, the energy value of butter is going to be equal to the energy absorbed by what? The water, right? And so that's what this equation, this heat that we're looking at, right, is related to the energy absorbed by water. She absorbed by water, which is equal to the energy released by the butter, right? That's the physical or the chemical intuition that we're using here, right? That these two things are related to each other. So we can use the energy absorbed by water because we know how to solve for that. And so when we plug in these values into our equation for heat, what values are we going to use? What's our value for mass for this? It should be 1900 grams, right? And why is it 1900 grams? Well, because we're looking at the temperature change of water, the specific heat of water, and the mass of water to give us the energy absorbed. To do that for the butter, we would need the specific heat of butter, the temperature change of the butter, and the mass of the butter. We are only given the mass of the butter. That's how you know which mass value to use here. So this mass value is what we're going to be using for our calculation of energy here. So that gives us 1900 grams, 4.184. What are the units of specific heat again? Joules per gram degrees Celsius. And then our change in temperature is going to be 11 degrees Celsius. Right, so these are all the relevant quantities that are given to us in the problem, so that allows us to solve for energy. The important step here is realizing that we need to use the mass of the water, not the mass of the butter, because the mass of the water is actually what's changing temperature, what the temperature we're measuring is of the water. So we plug all that in, we get 1900 times 4.184 times 11, 4.184 times 11. Why is that? 4.184 times 11 times 1900. That gives us 87,400 445.6. What are the only units that are left over when we multiply all these? Joules, right? Because degrees Celsius cancel out, grams cancel out, and we're left with units of joules, which is units of energy, which makes sense, right? Because heat is a unit, should be in units of energy. But we know we have how many sig figs in each of these quantities? 2 here, right? 2 sig figs. What about 4.184? 4 sig figs. And then 2 sig figs, right? So our final answer should have how many? 2, right? So we'll go Q is equal to 87,000 joules, right? We always include our units. And if we did that in scientific notation, how would we do that? Right, we have 1, 2, 3, 4. 1, 2, 3, 4. Yep, 8.7 times 10 to the 4, right? Because we moved the decimal place 4 digits to the left to give us a number between 1 and 10, right? So that's why we have 8.7. We moved to 4 places, which is why we have the 10 to the 4 there. And this is still going to be in units of joules. When we're dealing with scientific notation, we always remember that the sig figs is always given to us by the coefficient, right?
What was need to turn into?
No, I'm just doing that because I graded the quizzes this morning, and then also because we have the exam on Wednesday.
Will it be specified if we need to?
Yeah, I'll tell you whenever you need to. If a question usually doesn't say, make sure to keep track of sig figs. You can still do sig figs for that problem, but I'm not going to mark people down if they didn't get the right sig figs for it.
Yeah.
Usually, I try and remind you when you have, be aware of that. All right, so that gives us the energy of the absorbed by the water, right? But we're not done yet because we want to find what's the energy value of the butter in calories per gram, right? So we still have to go from this to calories, uppercase calories per gram, right? We still need to do that, so that's going to go on the next page. And we're just given a unit of energy right now, right? So I'm going to give you guys, we have 8.7 times 10 to the 4 joules, and we want to go to however many uppercase calories per gram. Let me give you the conversion factor for that and see if you guys can figure out. To joule to calorie. So 1 joule equals 0.123 calories. And again, 1 uppercase calorie equals 1 kilo lowercase calorie. So if you see if using those conversion factors, you guys can then get what we want, right? We want units of calories over grams. All right, so we're starting from 8.7 times 10 to the 4 joules. And we want to end with a certain amount of calories per gram. All right, so right now we notice we only have units of joules, right? So how can we get grams in the denominator? There's a couple different ways you can do this, but we'll just go over one way right now. This was the energy released, or the energy absorbed by 1,900 grams of water, and the energy released by how many grams of butter? 2.3 grams of butter, right? So if we want to get units of energy per grams right now, we take the total energy that's released by the total grams of butter that this energy was released from, right? Which, what that means is that we're dividing by 2.3 grams of butter, right? Because now we have the total energy released by the total grams of butter. When we take those two numbers, we end with the unit of energy per gram of butter. Right, so once you plug that into a calculator, you get a number, and that number is in units of energy per gram. Right, so that's how we get the grams in the denominator here. We have to know this from the problem. From the problem. And now we just do unit conversions the same way that we did for just the energy unit conversion before, right? Except instead of changing gram or ounces into grams, we're only going to be changing the units of the numerator from joules to what? Calories, right? So let's look at all the different conversion factors we have. 1 kcal should equal how many lowercase calories? 1,000, right? The same way that a kilometer is 1,000 meters, right? So this is 1,000 lowercase calories. And so this gives us two conversion factors, 1,000 calories over 1 kcal, which is the same thing as 1 uppercase calorie. And then 1 kcal is 1,000 calories. We also get two conversion factors up here, 1 joule per 0.239 lowercase calories and 0.239 lowercase calories per 1 joule. Right, so those are all the conversion factors. And now we need to determine which ones to use to end with units of uppercase calorie per gram. All right, so this is where we're starting from. And the first thing we need to convert is to what? Do we go straight to kcals, or do we go to lowercase calories first or uppercase calories? All right, we're starting from joules per gram. The first thing we convert that to is what? What conversion are we given to go from joules to another unit? Lowercase calories, right? So then we're going to go from that to lowercase calories per gram. And then from that, we can go to kcal per gram, which is then very easily related to uppercase calories per gram, right? So again, similar to what we did before, except now we're just changing the units of the numerator here. Right, so what conversion factor are we going to use here? The left or the right when we're going from joules and lowercase calories? We should use the right. And why are we going to use the right? Yep, because the joules cancel out. 1 joule per 0.239 lowercase calorie. Units of joules cancel out. And then we go from joules to kcal. Are we going to use the left or the right? Left, right? Because we want the units of lowercase calorie to cancel out. So that'll be 1,000 calories per 1 kcal. And then what about kcal to uppercase calorie? What's the conversion between those? 1 to 1, right? So whenever you have something where one equals the other, that just means that you can interchange those units whenever you want. Right? We can do it explicitly just by doing 1 kcal equals 1 uppercase calorie as well, but that's a 1-to-1 conversion. You can just use those units interchangeably. So when we plug all that in, we get 87,000 times 0.239 divided by 2.3 divided by 1,000. And we have 2 sig figs from all the numbers that are given to us, 3. So our final answer should have 2 sig figs. So we get 9.0 calories per gram. Just making sure all the units cancel out, lowercase calorie, kcal, and then uppercase calorie. I know it's confusing going between calories, kilocalories, and lowercase calories. That's just the way the system was designed. All right, and then we end with what we want to, which is units of calories per gram. All right. Any questions on that? All right, does everyone understand why we divided by 2.3 grams here? Right, that's because that's the total energy released by the butter, which is equal to the energy absorbed by the water, divided by the total amount of butter. That's units in grams, so when we plug those in, we get units of energy per gram of that substance. And I know it's tedious writing down all these conversion factors and making this little flow chart, but again, if you start from there, it's a lot easier to end up where you're going. And so then it's also easier to start the problem as well. I know we like to do a lot of steps in our head, and we can, it works out that way, but then it's easy to get stuff mixed up that way as well. All right. And this value also makes sense because if you look it up, that's about the energy value, the calories per gram of fat that you get. So if anyone's into calorie counting or doing that, training for a fitness competition or anything like that, that's about what you would expect from fat, right? Fat has the most caloric content compared to sugars and carbohydrates and proteins. All right, so let's take like a 5-minute break, give you guys brain a rest. You can come up and ask questions. Continue. All right, again, so this was the last thing that's kind of related to exactly what's going to be on the exam. We're going to talk about now is expanding this idea of heat absorbed and released, and then including things like phase changes, right? So we've talked about chemical changes and physical changes a little bit. Let's review them real quick, right? So changes in physical properties of matter that do not involve a change in its composition are called physical changes. And so these physical changes, are something like going between, an aqueous phase or a liquid to solid, solid to gas, right? And we can usually know what physical changes are because they tend to be easily reversible. And what that means, if we make that change, we can kind of undo it going in the opposite direction, right? So if we think about solid, right, water, ice, we can melt it. If we lower the temperature again or increase the pressure, we can then turn it back into a solid. So those changes tend to be easily reversible. And chemical changes, conversely, are going to be something that's not going to be as easily reversible. And so when we're starting to think about energy of matter and whatnot, generally, as we go from something like a solid to a liquid to a gas, we're increasing the energy of that matter. Why? Because when something's in a solid, it has a lot of chemical bonds. That's a lot of potential energy that's stored in the chemical bonds. As we start to break those bonds, the energy is released from the chemical bonds and then turned into kinetic energy or energy of movement, right? And that changes the temperature of the system because those are related to each other. And so this process is, depending on which direction we're going from which change is going to be related to adding or taking away energy of the matter. And so as we go from solid to liquid to gas, we're increasing the kinetic energy of the matter. The same way if I'm holding a ball right here and I'm not releasing it, it has a lot of potential energy, but no change in temperature because the ball's not moving at all. As I release it, the potential energy gets converted into kinetic energy, it falls, and then that would be like if a solid, you have two atoms bonded to each other, you break that bond, now it gets kinetic energy, and we know that the temperature is related to the kinetic energy of the matter. All right, so we tend to get more and more energetic as we go from something solid to something gaseous. And for chemical changes, so these are going to be anything that changes the composition of the material. And so that's called a chemical change. And chemical changes are not easily reversible. That's because if we change reactants, products, we'll learn about what these reaction arrows mean, right? They usually go up or down in energy. So it means we either have to take energy away from the system or put it in just to get the chemical reaction to happen. And these are not going to be easily reversible. Breaking specific bonds of a molecule and forming new bonds takes a lot of work compared to a physical change where it might just be, heating it up or cooling it down so that we're not breaking chemical bonds, we're just breaking what we call intermolecular forces, which we'll spend a lot of time on in a couple weeks. And so these are not going to be easily reversible. But you can tell this is a chemical change, right? Because we start off with two different types of materials in a mixture and undergo a chemical reaction to form a new compound. All right, so those are chemical changes. And then we've talked about some examples of those. We already went over those. And so this, going back to physical changes now, we can undergo a change of state. And so what happens in a change of state is that the matter releases or absorbs energy without a change in temperature. And so that might sound a little counterintuitive, the way that we talked about heat before. But if we think about it, if we are freezing water, right, it gets down to 0 degrees Celsius or 32 degrees Fahrenheit, and we keep cooling it down, keep adding, taking energy away, the temperature never drops below freezing until you've changed all of the water into ice, right? Or if you've ever measured the temperature of boiling water, right? You keep heating it up, you're adding more energy because it's still on a hot fire. If you put a thermometer in there, you'll see that it reaches 100 degrees, and it stays 100 degrees until all of that water has been converted into gas, right? All of it's been converted into water vapor. And so what's happening is we talked about how there's different energy levels for gas, solid, or liquid. And at a certain point, once you reach the change of state or the phase change for the material, energy isn't going into changing the temperature anymore. It's going into converting it from liquid to gas molecules. And so you have to add energy to do that. And so what are the different changes between these different states? Well, if we go from a gas to a solid, that's called deposition. We go from a solid to a gas, that's called sublimation. So something can sublime if it goes straight into the gas phase. A gas to a liquid, does anyone know what that's called? Condensation, right? We think about water vapor outside of your cold glass of water. Water condenses on the glass. That's why you get droplets on the outside. Condensation. Going from liquid to gas. What's that called? Evaporation. From liquid to solid. What's that transition called? Freezing. That's the freezing point. Freezing. And from solid to liquid, what's that called? Melting point. So those are the different phase transitions between the three states of matter that we care about. And what happens is once you reach that special temperature that changes from one phase to another, so 0 degrees for water goes from solid to liquid, right? Energy stops being put into the change of temperature of that material, and at that point, it starts being converted into energy that's required to then convert from one state of matter to another state of matter, right? So these are eventually going to lead to heating and cooling curves where we can plot the energy that's being released or absorbed versus the temperature, and we can see exactly how this works. All right, so here we have an example of what a heating curve looks like. So this can be water, for example, and we see we have heat added, right? So heat added should be in units of what? What are the units of heat? joules, right? Because it's a unit of energy. As we add energy to the system and we measure the change in temperature, when we're at the special temperatures, we're going from one state of matter to another. We reach this point, right? So as initially, we have, from point 0 to point A, for example, Q equals ms delta T, right? Before we reach the point where the change of physical state happens, we have a certain amount of substance, a specific heat, and a change of temperature. We're adding energy, right? So there's the energy added, right? We're adding energy to the system, and when we add energy, the temperature changes, right? And that temperature changes based off of whatever the specific heat is, right? So if it's, a lower specific heat, this line will go down that way. If it's higher specific heat, that slope will kind of go up. That's not that important, but the only thing that's important is that it changes, right? As we add energy to the system, we expect that the temperature changes. Once we reach the critical point, so from A to B, we see that the temperature stops changing, right? So why does the temperature stop changing? Because now the energy that we're adding to the system isn't being converted into temperature, because it's being used to do what? Not necessarily cool down, right? Because it's flat, right? So the temperature isn't changing. The temperature isn't changing at all, right? Damn chips. The temperature is not changing at all, so where is that energy going? Yeah, it's converting, in this case, solid water into liquid water. Q is going into converting solid to liquid water. Right? Because we have a lot of potential energy that's stored in this, solid molecules because they're close together, they're tightly bound. That energy is now being added, and it's not going into making them vibrate faster. It's going into physically breaking those solid water molecule bonds to then convert them into water molecules. Right, and so we'll talk about how does that actually show up in Q. Right, whenever we're in between states of matter, right, the energy that we add to the system is going to changing the temperature. But as soon as we reach this point where the physical state changes, that energy for a while is being converted just to going from one state to the next state. And so how that shows up is in what's called the different heats of vaporization, or the heat of melting you might see for these different things. And what that means, or heat of fusion, for example, is a specific quantity, so a physical property of the material. So for going between solid and liquid, we have a heat of fusion. And what that says is how much energy is required to melt 1 gram of solid, or in this case going from 1 gram of ice to 1 gram of water. And so this heat of fusion is then related to the heat. It's given in units of calories per gram. Right? Calorie is the unit of what? Energy, right? And heat is measured in units of joules, right? Units of energy, right? So if the heat of fusion is given to you in units of energy per gram, what quantity do you think you have to multiply that to get the total heat, for example, of melting all of this ice into water, liquid water? Right? How would you get that to cancel out? How would you get grams in the denominator here to cancel out. What would you need to multiply that quantity by? By a mass, right? So you need to multiply the mass times the heat of fusion to end up with just units of energy, right? Q is just units of energy. Heat of fusion is units of energy per gram. So you need to multiply that by a mass to get those to cancel out. And then you're just left with units of energy. And so this would just be the heat of fusion, or the heat absorbed or released during melting or freezing of water, right? So the sign of this depends on which direction that you're going on. And what does it say? It says, well, this is the energy required to melt or to freeze 1 gram of that substance, right? So this is also going to be specific for the material or compound. So the same way the specific heat tells you how much energy is required to change 1 gram of this substance by 1 degree Celsius or Kelvin, the specific heat of fusion is saying how much energy is required to go from 1 gram of solid of the substance to 1 gram of liquid of the substance. Let's see. Right, so it's the same idea. We're still looking at how energy moves, between a system and its surroundings. The only thing that's different now is that we're not changing the temperature anymore at these special temperatures. Why? Because we're converting the material from one state of matter to another state of matter, or vice versa. We also have the heat of vaporization, right, which is how much energy is required to evaporate or condensate 1 gram of that substance. And so this is called the heat of vaporization. And this is similar to the heat of sublimation, except now we're going between liquid and gas, or heat of fusion, except we're going between liquid and gas rather than solid and liquid. And so it's going to be also specific to the material or compound. And when I say that, really all I'm saying is that the same way you look up a table of the specific heats for how much energy is required to change the temperature of water by 1 gram of water by 1 degree Celsius, you would look this up for water, ammonia, iron. They all have their own specific values here. So people dedicated their lives to just getting those values in a table for you. And so then the heat absorbed or released from vaporization or condensation would just be the mass of that substance times the heat value of that as well. And again, this is because once we reach these special temperatures where we go between these two states, we have to account, well, now energy has to be used to convert from one state of matter to another state of matter, and vice versa. So energy has to be used to go between the two states. So it's like a pause in our change in temperature. Which means if you start at ice and you say how much energy is required to then change, ice at 0 degrees to water at, let's say, 32 degrees, you first have to calculate how much energy is required to convert all of that ice into water. Then you add it to how much energy is required to change the temperature of that liquid water from 0 degrees to 30 degrees. And so here, if we have a curve like we did before, like the temperature versus the heat added to the system, and we want to go between, or we want to ask ourselves how much energy is required to go from 0 degrees ice to 100 degrees steam. What that looks like on the plot is we start initially, if we started exactly, let's talk about not 0 degrees, but let's say -5 degrees Celsius of ice. So initially, we have to heat -5 degrees of ice to 0 degrees, right? Because once we hit 0 degrees, we're at that special temperature. Then at that special temperature, all the energy is used to convert the ice into liquid water. Once we've converted all the liquid water, or all the ice into liquid water, now the energy can go back into changing the temperature of the water. Right, so now we can go back into changing the temperature of the water until it reaches what temperature? 100, right? Once it starts changing state again from liquid to steam. And then once we reach 100 degrees, we want to convert all of it to steam. So now all the energy that we add is just converting it from liquid to gaseous water. And we want to ask how much energy is required to do this whole stepwise process. All that means is we're just adding up the energy at each individual step. So the total energy that we added is first heating the ice, right? Because we're heating it from -5 degrees Celsius to 0 degrees Celsius. So you go first, the amount of energy required to heat the ice. The next step was the amount of energy to do what? What was this flat line here? Converting it from ice to liquid water, right? So this would be Q of fusion, right? That's just the fancy way of saying converting it from ice to liquid water. Then once everything's converted to liquid water, we keep adding energy. What does that do to the liquid water? It heats up, it changes the temperature of the water now. So now we're changing the temperature, heating water, or the liquid. So now we're heating the liquid. And then finally, to get everything to go to steam, once we reach 100 degrees, what does all the energy go into? Yep, the vaporization, or turning all of the liquid water into gaseous water, right? Because once you reach that special temperature, temperature stops changing, energy is just going into converting from one state of matter to the next. And so this, if we actually had to calculate, we were given specific values to do that, which we don't have time to do today, but we'll do next week when we come back and finish up this lecture. This would be equal to ms of ice delta T, right? So the mass of ice times the specific heat of ice times the change in temperature, which is -5 to 0 degrees. We add that to the mass of ice that's going to be melting times the specific, or the heat of vaporization. Then we add that to the mass of water times the specific heat of liquid water times the change in temperature. And finally, we add the mass of liquid water times the heat of vaporization. Right, so we're just going over conceptually what the idea is here. We'll go, when we're doing it in practice, it'll make a little bit more sense. But the idea is if we want to go through, calculate the energy that's required or that is flowing in or out of the system when there's changes of state, right? We're going through one state of matter to another. We have to account for now the fact that some energy at specific temperatures is required just to go from one state of matter to the other. And so when we do go through this whole process, all we do is we just break it down into each individual part, right? So these problems, the thing that's challenging about them is just, okay, I have to account for first the temperature change of the ice, then the fusion of ice, then the temperature change of water, then the vaporization of water, and then it could keep going on because what if we wanted water vapor at 300 degrees Celsius? Then you would need another term for the change in the vapor of water as well. Okay, so we'll end there today.